This video is about wideband SDRs on the FM band 88 to 108 MHz. What you see is the cable from the antenna comes in here and goes first to this box, which is a 20 dB directional coupler, into which I can send some additional signal to add to what is on the FM band. Then there is a stepped attenuator, followed by a filter that allows through only the FM band. After the filter is a 3-port hybrid. It isolates the 3 outputs from each other and delivers a signal that is 5 dB attenuated, because it's split into 3 equal parts and a factor of 3 is 5 dB. The splitter is this thing. It's from Mini Circuits. The output one is going into the blade RF to the B200 converter board, and then after that, of course, into the blade RF itself. Another output goes here, and that is a PCIe 9842. And the third output goes here to the oscilloscope, where you can see that the peak amplitude is about 2.5 millivolts. I have now connected the cable that was previously on the oscilloscope to the spectrum analyzer. There are of course several stations here. The strongest one is about minus 58 dBm. I can make the span a little bit less. And here you can see frequency, what we have on the FM band in my location. Peak surge, and the strongest is minus 60 dBm. The oscilloscope as well as the spectrum analyzer are matched to 50 ohms. The distance to the nearest FM transmitter is 11 kilometers, and the second nearest is 27 kilometers. I click on the Terracom map, and then I get information about what the performance is of this station. It has 2 FM channels with a power level of 6 kilowatts or 10 kilowatts. And the second nearest one is this one with 4 kilowatts. And if I zoom out a bit, there are other transmitters. The one here, which is, it has 60 kilowatt on several channels. So that is, none of them is really very close, and this is a normal rural location or semi-rural for listening to the FM band. And the antenna is inefficient. It's not a directional antenna at all, and it's not resonant on the FM band. This is the antenna. You can see the thin wire here, just wound around some isolated cables, and then it goes up to the 3 that you see here. So it is just about 6 meters of wire 20 meters away from the building. And what you see here is the reminders of my 2-meter system. It's just a tower in the horizontal position. But I have good coaxial cables out to this place. The upper screen here is the blade RF. It's set to 25 megahertz sampling rate. And you can see the entire FM band. At 89 megahertz, there is a sweeper that sweeps 1 megahertz pretty slowly. It's a signal that I have injected. It has the same level as the FM stations, minus 60 dBm. On the blade RF, we have a mirror image. It comes at 107 megahertz. That could be removed by calibrating the Leanrad SDR. There are false signals about 1 megahertz above and 1 megahertz below. The lower screen is the PCIe 9842, and it stops at 100 megahertz because the sampling rate is 200 megahertz. There will be aliasing the station at 100.4, which you see here. It aliases in at 100 minus 0.4. It's this signal. And there are not so many signals above 100 megahertz here. We can see weak signals, a lot of them, in the blade RF. Above 94, for example, where I have them hover with the mouse, there is a lot of signals here that do not have counterparts so much down here. There is a signal in the PCIe at 92.6 or 7 or so, and that would correspond to the signal up here at 104.3 or something. To make this comparison, I have set the gain for the blade RF very low at minus 12 dB to match the sensitivity of the PCIe 9842. The S meters show about 25 dB, both of them, and they have the noise floor at the same level. If I click on the pure noise floor, let's say here, you can see it shows 0 for the blade RF, and for the PCIe 9842 it's also 0 for the noise floor. Now I have inserted a low noise amplifier to get a stronger signal into the PCIe 9842, and you can see the S meter graph shows now about 48 dB, and the noise floor I have set it, of course, to show 0. So I have 48 dB signal to noise on this one of the strong stations. The blade RF has now also the noise floor at 0, but the same signal is 40 dB. So the noise figure is now 8 decibels worse for the blade RF than for the PCIe 9842 when it now has the wideband low noise amplifier. The big difference between these two systems now is the big number of false signals in the blade RF. You can see here between 93 and 94 there is a forest of lines, and also here around 98 and everywhere actually. And it is also easy to see the sweep generator with its characteristic pattern. It has these false signals 1 megahertz away and something here at 96.2 to 4 or so. And here is something that goes the other way. It has the same level as this signal. They are symmetric around 98 megahertz. So they could be thought to be the signal and the mirror, but then there should be a different amplitude between them. So I cannot explain the source of these, but we wouldn't like to see them. I switch off the PCIe. I can now press S to save the 25 megahertz wide spectrum. S, and I give it a file name, let's say just X, and start to record. And the time is 1945.45, and I have the program in the background. I hope it will be comparable to my voice. And to see whether there are any errors in the recording, it is good afterwards when I play it back to look at the sweep generator, because that will show hacks if there is missing data. And I will leave this running for a while, and in the meantime have a look at the indicators of Microsoft. For example, here, and we are running with physical memory usage of 4 gigabytes, and about 30% of the CPU resources are in use. The resource monitor, let's see. It is telling something about the disk usage. It tells me 1 gigabyte per second. And disk, it says 53% highest active time, 55%, 89%. So it is probably okay, but much more than this is not going to be a good idea. And I don't know what's the cause of this pattern looking different from time to time. But now I've been recording for 3 minutes, and that should be enough to detect if the recording is okay or not. So I can switch off here. I have to give Linrad focus and press S. And then to play this recording, I have to create a file, new, default in Linrad is to place files in this directory, Linrad data. And I named it X, and it comes as x.raw. And that's it. File, save as, and I save it in the Linrad directory as ADFILE. And now I stop here and go to the main menu, press 1 for the first file that is named in AD file. And that is 1. Oops. I placed this file in the wrong directory. Save as. Linrad Blade RF. Save. And then 1. And I want to run in FM mode, E. And I don't want to repeat this. And here we are. And I listen to the same station that we listened to before. And I don't hear any problems. And nothing problematic is visible in the waterfall either. The hard disk is a 2 terabyte disk from WD. I don't remember what that is. Western Digital, I guess. It's a normal mechanical disk. And this shows that we can record the entire FM band with today's hardware without having several hard disks in a RAID system or something. It's enough to have just a modern standard computer. It would be very interesting for DXers in sporadic E openings to do this, provided the hardware would be a little bit less prone to intermodulation compared to the Blade RF. We would like to see normal modern hardware connected via USB 3 so we could have the bandwidth to do this. And I'm sure such hardware will be available in a reasonably near future. We would like to have a sampling speed of something like 250 megahertz. So it is a little bit above what has been normal today. And there hasn't been a single error as far as I can see. So this is encouraging. And here the recording is finished. The recording I just made is about 21 gigabytes, as you can see. That is about 1% of the 2 terabyte disk. So if I had allocated all of it to Windows, I should be able to record nearly 300 minutes. So that is several hours. That's more than a sporadic e-opening. Looking at the disk with this defraggler program, analyze it, you will see that there is a lot of fragmented files. If I look at it, it says one file in the block, and I click and I see it's x.raw, and wherever I click in this red area it's x.raw. The Windows partition is just a small fraction of this hard disk, so that's why it looks like much bigger than it is in relation to 2 terabytes. Fragmentation is 46%. That's a lot. It doesn't seem to matter because Linrad plays this easily. The nature of the false signals becomes obvious if I click on one of them. For example, here. So we can see it's a intermodulation product between the sweeping signal and one of the stations. And I try on another place. And it will be more obvious if I use a narrower bandwidth. And not all of them are heard because of the carriers that sweep by. And it will be the same up here. So it's obvious the signal level at this point is too high for the Blade RF. Now the Blade RF is running in sensitivity mode, which means that gain reduction is made in the IF while the LNA is running at full gain. Now there is much more gain to have. And as you can see, it does not make much difference because signals and intermodulation products and everything goes up to a similar amount. I have made the Blade RF screen bigger to make it easier to see some of these things. Gain mode is sensitivity, as you can see. X, and E, and I click on one of the strongest stations, and here you can see the false signal moving in the baseband, and it's about 30 decibels below this strongest station. and I reduce the gain, and you can see signals and intermodulation and noise, they all go down to the same extent. And here it's still about 30 dB between the very strong signal, well, very strong, minus 60 dBm, and the intermodulation that comes here. So now I change to linearity mode. Gain mode, linearity. And back to FM. And here we have the same situation as in sensitivity mode, because it's full gain. But when I reduce gain now, it will be the LNA gain that goes down first. And we still have 30 dB between this signal, minus 60 dBm, and the intermodulation product, or whatever it is, approximately 30 dB at least. And even if I go down, here maybe, so it is still 30 dB below that, approximately. I will now insert 10 dB attenuation.
Som vanligt den här morgonen så var jag på fiskemarknaden och jobbade när jag runt 8 på morgonen kände en mycket stark jordbävning. Det skakade mer än vad det någonsin gjort, så jag sprang hem för att se efter mina barn. Alla var i panik, berättar Gundia.
And increase the gain to get back the same level here. And the intermodulation signal is rather weak. And I continue to increase the gain. And here it is. And it's clearly weaker in relation to the to the FM station. But not much weaker. Here 10, 20, 30, 35, 40, something. So to find out better, I will use signal generators instead. I have now connected 3 signal generators, all of them at minus 60 dBm. One is the sweeping signal, as you can see, the first one at the lowest frequency, and the other 2 are the Hewlett-Packard 8657A, and they can be modulated with FM modulation. There are now 3 signals at minus 60 dBm. The screen shows far too many signals. This is not quite what we want to see. So I switch off now one of the signal generators to one at 100.2 megahertz. And then you can see 2 of the signals go away. And I switch it back. And then I switch off the other one, which is at 98.3 megahertz. And you see two of the signals come back. So we have mixing products of fairly high order. So the signals mix with each other, all three. So I switch off also the other signal generator. And now there is only the sweeper. And I remove the sweeper also. Like that. And we can see there are spurs, and they are about 10 dB above the noise floor in the main spectrum. The B200 has antenna input here, and then there are switches, so one can select different filters depending on what frequency one wants to listen to. And there is a user filter, which right now only is a cable from here to here, and where it's intended that the user can put whatever filter he desires. The idea is that I should have put this 88 to 108 MHz filter instead of this cable. Now I have bypassed this input switch and connected the hybrid, 3-port hybrid here, directly to the mixer, because I have the filter in front of the hybrid. Bypassing the input switch reduces the spur levels significantly, as you can see. And switch back the sweep generator. And the signal generators. And this is what we have. Now, to understand the order of things, I reduce the amplitude by 10 dB at 98.3 megahertz. And they go down by 10 dB, it seems. 10 dB. I go up 10 more dB. There. And that's odd, isn't it? So I go down and down again, and it will be more visible if I stop the sweeping, or I make the sweeping much. This is now sweeping half a megahertz. I make span 0.05 megahertz instead. So increase 10 dB. And you can see in the upper spectrum, the main spectrum, a lot of false signals, while the particular ones I was looking at, they have been reduced. So I go down and go down again, and go up, and then the other generator, increase the level, or decrease the level, decrease again. So what I can say is that minus 60 dBm, that's too much. I will now switch in the attenuator to make all the signals minus 70 dBm. And this looks good. Now I attenuate. And here we have the interference again. Going from 21 to 18 dB gain in LINRAD in linearity mode means reduce the LNA gain and increase the IF gain a little bit to get the desired gain change for the total gain. And this is now minus 70 dBm, and as I showed in the beginning of this video, the FM stations are 10 dB stronger than this, and I don't live very close to any of the transmitters. The lower part of the screen is the blade RF. The upper part of the screen is 2 AirSpy units. I had to switch to Windows 8.1 because Windows 7 does not support running 2 AirSpys at the same time in LINRAD. Not today, December 2014. I will switch off the signals by adding a lot of attenuation with the switched attenuator. And you can see from the S meter that the signal to noise ratio is about 3 decibels better in the AirSpy. And there is also obviously many more false signals in the blade RF. I can increase the level of the sweeper. I do that by 10 dB now. And you can see we have problems both in the AirSpy and in the blade RF. But the second AirSpy, which has the sweeper outside the visible passband, it is not affected. There is a filter removing this signal. The upper right is an SDR play, and the upper left is the AirSpy, and the lower screen is the blade RF. I have set the SDR play for the similar noise figure as the one of the AirSpy. The SDR play has a filter and it's sampling at 5 MHz. So the sweep signal is outside the window. I can increase it by 20 decibels. Like that. And you can see on the other radios that this is a disaster. It does have an impact on the SDR play also. But I could set the bandwidth smaller in this display and probably get rid of this problem. So wide bandwidth has a cost. The strong signals are let through all the way to the AD converter. The reason for the very poor performance you have seen so far is that the tuners are not designed to be used as wideband receivers. They have IF filters, and since the IF is very low, these are on low frequencies. I have set the IF filters to the narrowest available bandwidth in the SDR play, where it is nominal 200 kilohertz, and we can see on the spectrum upper right that it is plus minus 200 kilohertz, so we have 400 kilohertz bandwidth, and that is reasonably well fitted to an FM station. The Blade RF, the narrowest bandwidth, is about 2 megahertz, and it's designed for digital modes, so it doesn't have a narrow filter for FM, but it does help quite a lot because most of the FM band is outside this range. I'm listening to a station at 93.8 on all these tuners, and the AirSpy does not have the filter enabled. I use it as a monitor to see where I have the variable frequency and also to demonstrate it. The variable frequency has the same level as before, minus 60 dBm, and I tune it slowly. And without the filter we would have spurs. You can see in the AirSpy we have a spur here, a mixing product. Because there is no filter in the AirSpy yet. And here is another one, but you see nothing in neither Blade RF or in SDR Play. I thought I heard something, but that was just the way the music was playing. Now you can see the signal approaches the passband of the Blade RF, and then we have some non-linearity. You can see the signal generates overtones outside the passband. It means it is too strong. But and we can avoid it by moving the passband and then also moving the point in the passband where listening is happening. Now what is more interesting is I can now increase the level by, let's say, 20 decibels. 10, 20, and move the frequency again. And you can see this is not good for the AirSpy, as I showed before, but the other two, they have the filters. Interference is not strong. Here is something in the Blade RF, but it's weak. And all the way until I come near the passband, things work fine. But no longer. Here is total saturation. So I listen to the SDR Play instead, and of course it has a narrower passband, so it's not as much disturbed. It starts here where there is a spur, And you can see we can listen to the station until the signal comes very close. But there are occasional... This is the mirror image, I would guess. Yes? No? Well, I'm not sure. So the purpose of this sequence is to give you a feeling for the behavior. I'm not doing precise measurements. I have not yet implemented the filter in the AirSpy, but it should behave in a similar way. The bandwidth is not as narrow as in the SDR Play. I don't remember exactly what it is. You can find the data sheet for the tuner that is being used. I bring the signal level up. First, put the frequency far away. Let's say we are on 93.8, so I go on, let's say, 90 megahertz. That's nearly 4 megahertz away. And I bring the level up until there is a problem. And you can see the noise floor goes up in both tuners by similar amounts. And if I tune the frequency a little bit, I go downwards. There is some differences. At larger frequency separation, the blade RF is the winner. And if I go for a closer frequency separation, so here is a mixing product of some kind. There is a spur. But at close range, of course, the SDR Play is the winner, but this signal is too strong. It is now minus 30 dBm. But I can reduce gain. And it doesn't help. It makes a small. I can hear it, but not well. So I have to reduce the interference level. So for the SDR Play, the level is now minus 40. 39.8, minus 40 dBm into the tuner. And that's the point where weak signals start to deteriorate. And it's similar for the blade RF, but the permitted frequency spacing is quite a bit larger because of the wider filter.